Alrighty, so right now we're going to be doing chapter 20 for physics 102. Alright, so it's going to be physics 102. This is going to be chapter 20, which is going to be electric circuits. So let me actually go ahead. So, in an electric circuit, an energy source and energy-consuming devices are connected by conducting wires through which electric charge moves at. Now, the first thing we want to define is your current. Now, when charge flows from one place to another, an electric current is formed. Now, most practical applications of electric phenomena are based on our understanding of electrical current. Now, your electrical current is how many charges per second do you get? So, which is basically how many coulombs per second. We call that the amp. So, let me go ahead and define the first one. Actually, let me define these. The voltage, which we give it letter V. Now, your voltage, that's your electric potential. Which is your potential energy per unit charge. Which is, we actually seen that before, which is how much joules per coulomb, which is actually your work over your charge, Q, which that's what we give the volt. So this is the unit for this volt. Charge, your work, joules, coulomb. So we talked about the voltage, which is your electric potential, which is your potential energy per unit charge. So it's how much work per charge, which is joules per coulomb. We actually learned, and then we just defined your current. Let's just write the current over here, which we give it a big letter I. Now your current, that's what we, let me actually get a different color for this one, for the current. Now that's what we just saw a little while ago, is how much charge we have per time. So is how much charge you have per time. So let me just write this down. Charge per time. Which is how much charge flowing past a point. In a circuit, point in a circuit in a second. So it's how much charge flowing past this point in a circuit in a second. The third thing I wanna define is the resistance. Which we give it a big letter R. Now your resistance, go back and write on this one, is how much charge flow controlled. How much charge, how much current you flow, charge rate, controlled. Now the unit for it is the ohm. Now, going down, let's define something called Ohm's law. So we talked about ohm. So let's define Ohm's law. Ohm's law which is, let me actually write this down, which is named after George Ohm. I think he died in 1954. Now, this Ohm's law states that your current is going to equal your voltage divided by a resistor. So your voltage equals IR. So let's explain this. Imagine if you have a pipe, and I don't know, there's a closed door on that pipe, and you have, let's say you have water in there, right? So because this is closed, on the top, what you're gonna have a potential energy for that water to go down. Now, as soon as you actually come in and you open up the gate, what's gonna happen? Your water is gonna start gushing out, right? Now, let's say you take that same pipe and you actually take it and you squeeze it down. Let's say like this, down the middle. So what's gonna happen, right? So you're gonna have water over here, you'll be able to have water here. In the middle, you're gonna have a little flow. Now, the flow rate on both sides is the same. So let's say this is the door. When you open it, and here's your water comes out. That's how the current works. When you have the door closed, the current, you're not gonna have any flow of water. When you have the door open, you're gonna have a flow of water. If you even try to squeeze it, the flow coming in is gonna equal to the flow coming out. So let's say we have a circuit. Now let's define some stuff first before I do this circuit. Let's say you have a battery. Drop better battery. That's your positive, that's your negative side. So drawing a battery, the longer line is always the positive and the shorter line is always the negative. So let's say this is actually 16, let's say it's a 16 volt battery. So that's how you draw it. Now, drawing a resistor. Resistor, you go in, quickly line. Now, when you have a wire, the direction that's done on the wire itself, that's your current. So let's say if we actually go ahead and let's say we draw a circuit. So I don't know, let's say we have a circuit, let's say you have a resistor right over here, and then you have a battery going in, and let's say you have our little switch, our little gate for our water. So let's say you have a little switch open. that actually closes this way. So this is your resistor. This is your battery. You're going from the long one is always positive. The short one is always negative. And you got the current going. Let's say it's going this way. So the question that we have, let's say if R was, let's say 8 ohms. And let's say we use the same battery as we used on my little example a while ago. So this is 16 volts. So what is I? I is going to equal V over R from Ohm's law, which is going to equal to 16 over 8. So you're going to have 2 amps. Now, the direction usually goes from positive to negative, but the current does not always involve that. So the current does not involve the flow of electrons always. Yeah, so remember from last class, we actually said, let me actually make this bigger, that the charge goes, you get your positive, and you get your negatives over here. And the charge Q goes from positive to negative. Well, the current doesn't always involve the flow of electrons. So you might actually have a current going that way, or you might actually have the current going that way instead. Instead of going from positive to negative, it goes from over here when you close the gate all the way back over here. So it actually depends. Now, we talked about the resistor. So let me actually go ahead. So let's say you have a circuit. Resistor, your voltage going in. That's your resistor, that's your positive, negative, that's your voltage. And you get a current going this way. Now, from Ohm's law, your V equals what? IR. That means your R equals your V over I ohms. So what is R? Again, R is your resistance of the circuit. Go ahead, write this down, which is your measure which we said it was a measure of opposition to the flow charge. Now, basically what it looks like is it looks like a little cylinder. It has 2 wires coming out of it. So let me actually go ahead and get black. Your current I1 comes in, you're gonna have a current I comes out. Now, this is gonna be your length, and right over here, that's gonna be cross-sectional area A. Now, the resistance depends on the type of material that it's made out of, so the composition. The length, the longer the wire, the greater the resistance, the shorter the wire, the shorter the resistance. And it also depends on your area, your cross-sectional area of contact. Also, when you have high temperature, you have high resistance. So temperatures also plays a factor in our resistance performance. Now your ohmic materials, let me just write this down. Means it has an ohmic constant R. Which means it stays the same. No matter what voltage on the current I you put on it. That's where we introduce the resistivity, right? So let's say you got, I don't know, this is your resistor right over here, which this goes, that's your wires coming out of it. Your current going in, your current going out. Again, that's your length. And this is gonna made out of something called resistivity. So the resistivity, which we give rho, that's called resistivity, which is you resist to your current. The resistance for the material to the current. So for instance, your resistivity for copper is going to equal 1.72 times 10 negative 8 ohms meter. Resistivity current per unit. I forgot to put it down per unit. Resistivity current per unit. Resistivity for rubber is 10 to the 13th ohm meter. Yeah, let me actually write down that units for this. It's resistivity per to current per unit. So it'd be ohm meter. Now, I'm gonna introduce something called conductivity as well. So conductivity, let me actually get a color for that. So if you notice, the copper that rubber has a higher resistivity than copper, so it's actually better to conduct electricity with copper than rubber. Now, we're gonna do something called actually conductivity, which is your sigma, which means you allow current. Now your resistivity is gonna equal to 1 over sigma, and vice versa. Your sigma is gonna equal to 1 over your electric conductivity. So this is your, again, you get a red electrical conductivity. So the resistivity involved with what type, with the type of the material that's made out of, the type of if the resistivity is higher, that means you got a bad conductor for electricity. The resistivity is lower, that means you actually got a better conductor for electricity. That's what will bring us to power, which we're gonna give it the letter P. Now, when you go to the hospital, what do they give you? If you go, let's say this is a hospital bed, and you're in the hospital, God forbid, sit down. So what do they give you? They go and they put an IV on your arm, sit down over here, in order to get better. So when you go and you're feeling weak, you try to give you an IV so you can have more power. So your power equals your IV. P is your power, I is your current, and V, that's your potential difference, that's your voltage. So if we actually break it down, what we're saying, this one's gonna equal to, let me actually write this down. So your I, actually, let me just stick with green for a second. Your current, which is gonna equal to, again, we said it's amount of charge per time. So if we actually multiply this, what we're gonna have? We're gonna have the amount of charge per time multiplied by charge per time multiplied by your voltage V. Which the power definition by itself is what? Actually, let me get a different color. Power is actually what? Energy over time, right? That means, actually, let me rewrite this just a little bit. Actually, no, hold up. Let me just write this. Delta QV over delta T. So what you get? Delta QV over delta T. So delta QV, that's your energy. Again, Q is the charge, T is the time, and V, that's your voltage. Which is, this is the time also, delta T. Let me write down the T better. So delta QV, that's your energy, which is your energy per time. That means that your voltage is going to equal to so your voltage is gonna equal to your work. Again, your voltage is gonna equal to your work over, actually, let me rephrase that just a little bit so it won't be confusing. Let me get a different color. See, your voltage is how much work you do per charge. This is what we saw from chapter 19. So when you have delta Q over Q multiplied by the voltage, what you're gonna have? So actually, hold up, let me just adjust this for a little bit. Okay, yeah, better. So V equals your work. Let me just write this down. Work. Again, that's the charge. So V equals so when you actually have your charge multiplied by the voltage, what that means? Your charge multiplied by the work divided by the charge. Both charges cancel out, and what do you have left? You have left the work, which is your energy. So let me go back. So we said that the power equals IV. Now, I, we saw that is going to equal to V over R. And V, we saw that is going to equal to IR. That means substituting this, what you're going to have? I multiplied by IR. So you get I squared R. Or you can say your P, your power, it also equals IV, which if you substitute the I for it, we get V over R multiplied by your V. So you get V squared over R. Now your power also is gonna how much is how much energy per time. That means your energy is gonna equal to your power multiplied by your time. Let me go ahead and label these. Time, energy, and again, this is your power, which is the same as this. So let's say we do a question. Let's say how much resistance would be offered by a 12-meter copper wire with diameter of 0.01 meters. All right, that means our area is 0.01 meters. And you're looking for that diameter. So basically, this is our little resistor that we have. This is, let me get a different color. This is our cross-sectional area, which because it's a square, you get pi r squared. You find r is the area of the circle. You found out the area, and actually, hold up. Diameter, I'm sorry. The diameter was 0.01 meter squared. And we're trying to find the resistance. So again, is your R twice of that, that's gonna be your diameter. So your resistance equals your rho L over A, your length over the area. So resistivity, so that's copper, we said the resistivity of copper was 1.72 times 10 negative 8 multiplied by your length, which we forgot to write down the length in our information, which is your 12 meters, divided by your area. Actually, we don't even have the area, that was the diameter. That's actually corrected. Yeah, so divided by your area, which your area again is pi r squared. So this would be 1.72 times 10 negative 8. That'd be 12 divided by pi r squared. R is going to be 1/2 of this. So R is going to be 0.01 divided by 2, which is going to be 0.0005. So we get 1.72 times 10 negative 8 times 12 divided by pi multiplied by 0.0005 squared. Plug it in. And you should get 0.003 ohms. Now, let me actually go back over here. So the amp is named after Andre and Marie Ampere, which he died in 1836, and is the unit for the electrical current, which is how many coulombs per second. So let's say you have a question: how many electrons per second flow past a point in a wire carrying a current of 1 amp? Let's do this question real fast. You get 1 amp carrying current. Let me do this example. So you need the electrons per time, per second, that flow past that point, which is going to be your charge per time divided by your charge per electron, which is going to equal to both Q's cancel out. So what you're going to have? You're going to have your charge per time, which is going to be your current, so that'd be 1 amp, divided by your charge per electron, which is going to be your electron charge 1.6 times 10 negative 19 coulombs per electron, and you should get 6.3 times 10 to the 18th electrons. Here's some questions over here that you probably want to go through. So go ahead and do this question. How long can a 12-car battery with 60 amp capacity would power the lights? You need to find out the current and the time. Here's another question that goes through the resistor. Go ahead and solve that one. We also talked about the power, which is going to be your current multiplied by your voltage. Now the unit for electric power is watt. The commercial unit that we use is kilowatts per hour. So if it tells you what the greatest power is to a 15 amp circuit and 120 volts, it means your P equals IV, which equals to 15 times 120, which is 1.8 kilovolts. Here's another question. Go right ahead. Find the current for a 60 watt light bulb on a 120 volt circuit. You should get half an amp. Here's another question over here that you can actually also apply to what we did. Go ahead and solve it. Now, batteries was invented by Volta. So the normal potential difference in a car battery is 12 volts. A car battery is made of 6 cells with 2 volts each. And they are connected in series. Now, let me just go right ahead. So the electric current is the amount of charge per unit time that passes through the surface that's perpendicular to the motion of charges. And that's what we did. Now, if the charge moves around the circuit in the same direction all the time, the current is said to be direct current. If the charge moves first one way and then the opposite way, the current is said to be alternating current. Here's the question over here. Go ahead and stop it and go ahead and work on this question out. Make sure you understand where we're at right now. So resistance is defined as the ratio of the voltage applied across a piece of material to the current through the material. Now, your Ohm's law stated that your resistance equals V over I, or V equals IR. Now, your resistance unit is your Ohm. So go ahead. There's a question about resistance. Go ahead, pause this video and do this question real fast. Now, for a wide range of material, the resistance of the piece of material of length L and cross-section area is going to equal to rho multiplied by L over A. Rho, that's called your resistivity. Of the material as an ohm meter, your length and your area is L over A. So this is what you're gonna use when you draw a circuit. So the first one is 3 blue lines, that's your resistance, your battery. The long line is positive, the short line is negative. And you put them in together with the black line, with the arrow, that's your current direction. Now your resistance formula, not formula, your resistance depends on the material, type of material that's made out of, whether it's copper, rubber, and each material has a different resistivity. Length, the longer the wire, the greater the resistance. Cross-sectional area, the greater the wire's cross-sectional area, the less the resistance. And the higher the temperature, the more the resistance of the wire. Now, here's 2 examples. Go ahead and work on those examples. All right, now we also been through the power, which equals to IB. We went through this right now a while ago. Went through electric power. Also, now the power's unit is still going to be the watt. Now, when you have, let me actually do this over here. Let's say, and this is your graph, this is your time t, and you're going, let me actually go this. So up to here, let's say this is your V naught. And over here, that's your negative V, whatever V is, right? And this is gonna be your principal axis, so that'd be 0. Now, going in from top to bottom, actually, let me get a different color. Let me take this down a little bit. So going in from here, let's say to here. That's how your battery it is. That's your positive, that's your negative. Same thing. That's your positive, and that's your negative. Now, down here on the bottom is the opposite. So down over here, maybe is the opposite. So you start from your positive over here, this is your negative. Same thing for this one. Let's just say this one to this one, it'd be over here to over here. So this is your positive, this is your negative. That's how the battery looks like. Now, your peak, your V, your voltage, this is something. So your voltage is going to equal to your V naught sine 2 pi F T. T is the time. F, that's your frequency. Now, V naught, that's your peak. V naught, that's your peak. Now your current, which equals to your V over R. Go ahead and substitute this in, so what you get, V naught sine 2 pi ft over R. So your V naught over R, that's gonna be called that I naught sine 2 pi ft. Now, I naught kind of like the V naught was your peak voltage. This is your peak current. So when you actually say that your power is going to equal to IV, so basically be I naught sine 2 pi ft V naught sine 2 pi ft, which means be I naught V naught sine squared to 2 pi ft. Now, what we have is a sine square over a function. Sorry, sine square of a function over an integer. Which equals always to 1/2. So this whole thing is going to equal to 1/2. It's sine square function over an integer. Integer is 1. So basically your power is going to equal to I naught V naught over 2, which your I naught and your V naught this 2 is actually what? Your square root of 2 multiplied by square root of 2. So really, what we have is I naught V naught over square root of 2 multiplied by square root of 2. So basically what we have is I naught over square root of 2 multiplied by V naught over square root of 2. And that would be your I root mean squared. And this would be your V root mean squared. Let me just write this down. RMS is root mean square. Now, when you have two resistors in series, let's say you get, I don't know, this is R1, R2 connected to some kind of battery, right? And let's say this is your negative, this is your positive, that's your R1, that's your R2, and let's say you got I going in clockwise. So when you're actually dealing with series, your total resistance equals to R1 plus R2 plus R3, blah, blah, blah. So in this one, it'd be R1 plus R2. That means your total voltage, which is your V1 plus your V2, which is going to equal to your V1 it'd be that I, that current multiplied by R1, plus that I multiplied by R2, which is gonna equal to IR total. Now, that's in series. What about if they were connected in parallel? So let's say they were connected in parallel. So let's say it's connected like this, and you got another R coming in. And then so let's label these. Let's say you got two resistors connected in series, in parallel. So basically you got a current and a current. Let's call this one I1 and let's call this one I2. And here's your positive, negative, and positive. So you get two connected. Now, your total resistance will be 1 over R1, the reciprocal, plus the other reciprocal, 1 over R2, plus whatever. You know, how many R's you have. Your current is going to be your I1 plus your I2. You got, actually, let me actually rephrase this. So it's actually 3 nodes. So you get, this is your I. Let's just call this regular I. So this is going to split into I1 and I2. So your current equals I1 plus I2, which is going to equal to V over R1 plus V over R2 plus, well, you know, if you have multiple ones, V multiplied by 1 over R total. So let's do an example, shall we? So let's say we have a circuit. Say this is long, this is short, connected to a battery. So the first one is 5 ohms, the second one is 10 ohms, and this is 12, negative, positive. Now, taking this one, we want to make it condensed. So these are in series, there's no nodes between them, so the circuit would look like something like this. So this one would be 15 ohms, negative, positive. 12. Now your current is going to be V over R, will be 12 divided by 6, and you should get 2 amps. All right, let's do another example. Let's say, actually, we have a good example over here. Let's do the circuit. So there's 110, 180, 220, and 250. Let's do the circuit right now real fast. So we had one coming in there, one short one going in connected with one, and then we actually had one over here and one over here, 2 of them. Let me look at the numbers, 220, 250, 180, 220, 250 ohms. This is 180 ohms. And we got what, 110, 24, yeah. 110 volts, and this is positive, this is negative, that's your 24 volts. Now, the question is, reduce the total. So the first one we're gonna do these two right over here. It should be black. So these two are connected in series. So what you're gonna have? You're gonna have the 220 plus your 250. So it's gonna equal to 470 ohms. So that actually reduces our circuit to this one. So this one will be 470 ohms. This one's still 180 ohms. This was 110, not volts, ohms. I don't know why I wrote volts over here. It's supposed to be ohms. And this is your 24 volts, positive, negative. All right, now we got the 470 and the 180 that's in parallel. So we need to do this one. So let me actually go do this. So 1 over R total for this one is going to equal to 1 over 180 plus 1 over 470. Divided by 180 plus 1 divided by 470. And then what you're going to do, you're going to flip it. That means your R total I got is 130 ohms. So actually, we can actually redraw this circuit. To a simple, goes down from that one. So this will be 130 ohms along with our 110 ohms and the 24 volts. Now, we have these two in series. So it'll be 110 plus RT equals 110 plus 130. So you should get 240 ohms. So we really can actually redraw the circuit as 240 ohms. That's your 24, positive and negative. And is that what we had? Yep, and that's exactly what we have. Now, when we talked about, we touched this on it a little bit. Now, when you have a current going in, so let's say you have a wire, here you got, there's a first resistor and a second resistor. So, this is going to be your current going in. So let's say this is I1 comes down to I1 going in, and then I2 is your node. I2 comes over here. So because there's nothing going on, let me actually write this down. This is a node. There's nothing going on between the nodes. That means your total current is not total current. I'm sorry. Your first current, I1, is going to equal to I2 because there is no node going in. But let's say you got a node that's actually splitting into three ways. How does the current behave? Well, your I1 comes in, comes out, here's I1, and it's going to split into two I. So this is going to be I2, and this is going to be your I3. Your I1 is going to have to equal to your I2 plus your I3. Your in has to equal to your out. So your sigma IN has to equal to your sigma I out. So let's say you get a node and it's a four-way. So you get 1 amp coming this way, you got 1 amp coming that way, 1 amp coming this way, and let's say you go that way. Actually, let's go opposite. That means you get your first amp, your first one plus your second one plus your third one. Actually, let's just go this way. Yeah, so it'd be your first one, your second one, third one, plus I equal to 0. That means I equals to 3 amps. Actually, minus 3. Now, when you get a negative, that means that the current is going the wrong way. You just switch the current. Now, let's say you have. Actually, I will just do the example that's in the PowerPoints. Let's say you have a circuit like this, and you want to find out what is the current. So you have 5 and 1 with 12. That's what brings us to Kirchhoff's loop rule. So you have a circuit, you got 2 resistors on it, and you got your battery. You got a current going that way. And let's say this was 5 ohm, and it was 1 ohm, and if I'm not mistaken, it was 12. Yeah, 12 volts with this negative and this positive. Now, find the current. Now, with Kirchhoff's law, the voltage across each resistor is going to drop from the main voltage. So you got a current going in there. So you're leaving, let's say you're going in there, so you're leaving at a positive. So be 12 volts is going to equal to. Now, once you leave the positive, that means it's going to become negative. Your resistance is going to equal to negative, not equal to. I'm sorry. So 12 volts minus 5 I's minus 1 I. Remember, your V equals IR, so that I multiplied by V. When you go with the current, you come out, the battery comes out the same side as the sign. So this is coming out in the positive, so this is 12. That means you're dropping on the resistor. So be minus 5I minus 1I is going to equal to 0. That means your 12 volts is going to equal to 6 I's. That means your I is going to equal to 12 divided by 6, which is 2 amps. And that's what we got. So for Kirchhoff's rule, the sum of the magnitude of the current directed into the junction equal to the sum of magnitude of the current directed out of the junction that we just solved. And a random enclosed circuit, the sum of potential drops equal to the sum of the potential rises. So let's do another example, shall we? Let's say we have this little circuit right now over here. So we get a battery along with the battery. It's negative, positive. That's your negative, that's your positive. You go from 12 to 8. And we're going this way for our direction that we decide. Now, if you actually work this out, doesn't matter the direction. Once you work it out, if your current comes out negative, that means it's actually going the other way. If it comes out positive, it means you actually chose the right way. So let's say we're going that way and we want to find I. This 24 volts and this 6 volts. So let's say you want to find I. All right? So you go in, this is coming out as 24. You're going out from the positive. So your first resistance, which is 12 ohm, So you're coming from positive, that means that is gonna affect that negatively. So it'll be minus 12I minus 6 volts minus 8I is gonna equal to 0. That means 24 and 6, that's 30. All right, so we got 24 minus 12I minus 6 volts minus, actually, let me get the volts out the way, nobody would get confused, minus 8I. Again, your V equals IR, remember that. So, what you have? You have 24 minus 6, which is going to be 18. So your I minus 20I equals minus 18. That means your current is going to equal to 18 over 20, which is going to equal to 0.9 amps. And that's what we got. Now, let me go ahead and watch a little video real fast that talks about capacitors. Alrighty, so this one talks about the capacitors, which is your charge per volt. Voltage. Now, two parallel lines, that's a capacitor. Two parallel lines going in. Now, when you have parallel capacitors, it's the opposite of resistance, so parallel. So that means you got a capacitor going in this way, you got a capacitor going in this way. The equivalent capacitors is going to be, now with resistors, what we did is 1 over reciprocal. This is going to be, let's say this is C1, this is C2, be C1 plus C2. When they're actually connected in series, let's say the C1, C2. So our capacitance then, 1 over capacitance total is going to be equal 1 over C1 plus 1 over C2, etc. Now, let's do one more example of a circuit to find using Kirchhoff's rule. So let's say you have this this circuit. Let's say this is 10 ohms. Let's say this is 20 ohms. And let's say this is 20 volts, which this is your positive negative, this is your positive negative, and this is going to be your 10 volts. So this is your V1, let's call this your V2, and this is your 40 ohms. So let's say this is your node A, this is your node B. And let's say the current is going this way. So basically you got I1, that's going to split into I2 and I3. I'm sorry. So basically you get current I1, current I2 that's connecting to current I3. So your I3 is going to equal to your I1 plus your I2. That's your first equation. Now looking at the first box over here, what you're going to have? You're going to have, this is coming out of the positive. So what you're going to have, 10 volts positive. That means this is going to drop to negative minus 10I1 negative. And then it's going to go down here, which is going to be I3, again, connected to a negative. So minus 40, I3 is going to equal to 0. That's the second one. The third equation, right now we got 3 unknowns, so we got 2, we need a third equation. So with our third equation, you're going this way. So again, your 20 is going to be positive, minus 20 I1, I2, minus 40 I3 is going to equal to 0. Now, let's take equation 2. Let's solve for equation number 2. That means your 10 minus 10 I1 minus 40 I3 equal to 0. Move this to the other side. So what you're going to get? 10 I1 is going to equal to 10 minus 40 I3. You can divide all sides by 10. So what you're going to have? You're going to have I1 is going to equal to 1 minus 40 divided by 10, which is 4 I3. Let's call this equation 4. Now let's do the same thing for equation 3. Take equation 3 and divide it by 20. So what you're gonna have? So your I2 is gonna equal to, I2 is gonna go over there. What you're gonna have? 1 minus 22. 1 minus 2I3. That means you substituted in 1. So I3 is going to equal 1 minus 4 I3 plus 1 minus 2 I3. That means you get 7 I3s is going to equal to 2. That means your I3 is going to equal to 2 divided by 7, which is going to be 0.2857 amps. Substitute it back in there in the I3, so that means your I2, which is 1 minus 2 I3, so it'll be 1 minus 2 times 0.2857. So this will be 0.6, so it'll be almost 0.43 amps. Your I3, if you calculate it, you should get what? 143 amp. And that should conclude chapter 20 for Physics 102. If you have any questions, just email me at abunaem@uah.edu, or you can contact me, call me or text me at 256-348-1480. Thank you.